as I was saying, there are some people who are the audience of this little mini seminar who are not here physically, but who will be watching it online. So there are other people who have registered that are not here. This is part 1 of 2 of healthcare statistics, and it's really an introduction to what is available in statistical analysis. And this first of the 2 is about what's called Frequentist Statistics, which is the most commonly known statistics. And so if you just move on. And so we've come a long way in healthcare from, as you can see in those images, from cutting people open to having a room full of people looking at the innards, to modern medicine, largely through improvement and constant intervention in healthcare to make it better and better and better and better and better. And a lot of that is done through the examination of data. Next one. So in health, we do something, we intervene. And so the quote there says, do something if it works, do more if it does, and if it doesn't do it, do something else. And that's typically what we do, and whether that's in the research area or in the quality improvement area. And we try and do it well. We try and do it ethically. We try and do it with respect to patients. We try and do a good job of it. Next one. So our intuitive sense of change or measuring our intervention is we test something, we try and get a baseline, we do our intervention, and then we measure after the intervention. And so that's a very simple kind of model, and you might do that in quality and quality improvement cycles. We do it in research as well. And then the issue comes, what does it mean if it's worked or not? How do we know if our intervention has worked? And so that's where the rubber hits the road with statistics and how we try and quantify what does it mean if our intervention has worked or not. That's next one. And there are a couple of methods there. There's that simple before and after with the intervention in the middle. And then there is a control group. So you might have a control group in quality, do you sometimes? Or not? You just try and improve the system.
Yeah, we try and improve, yeah.
You try and improve everything.
Yeah, that's right.
Yeah. And again, so whichever way we do it, what does it mean if our intervention has worked or not? Next one. This is a complicated slide, and it's just got a whole lot of words on there. And I deliberately made this slide really complicated. And the idea was to frazzle your brain with all of the little things that enter your head when somebody tries to do some research and include statistical analysis in it. And so there's lots of ethical things there. There's data sets, there's the clinical significance. And what if I don't find anything? What are the implications of that? Maths really, patient privacy. I can't read everything, but anyway, there's a whole lot there. And all those words that are jumbled up there have come across my desk since I've worked here. So that I didn't make them up. These are the kind of things that come across our desk when we are attempting to do some research work and then do some analysis as part of it. Next one. Some considerations. This is part 1 of 2 stats presentations. The first one today is Frequentist Statistics. Frequentist Statistics. Try and say that really fast. Frequentist Statistics. It's quite And the other one is Bayesian statistics. And the Bayesian statistics approach is quite different to the frequentist one. Hello, Sharon.
Yeah.
Basically, in frequentist statistics, we assume that there's some measure of something we're doing, and it might be, some average, say an average age or something in a population, and we assume that that average age is a real thing. And then we take a sample and we test the hypothesis that there is a real thing there that summarises our population. It could be age, it could be anything in healthcare. Whereas Bayesian statistics doesn't do that. It doesn't say we assume there is a real summary of the population out there. We start with a human guess as to what that thing is that we're interested in. And it could be, let's say, age, or it could be something to do with healthcare. And we make an educated guess as to what it is, and then we collect data, and then we test our guess, and then we refine our guess. So Bayesian statistics has a little bit of more of a human input into it. And the little cartoon over there is a reflection of that, which I can't read, so I won't go into it. Let's move on. So in frequentist statistics, we typically take a sample from a population. So one of the main things I'm going to be doing now is talking about samples. Samples are all important. And it's also based on hypotheses. So there is in regular statistics, whether it's in front of you or behind you, or behind the scenes, I should say, there is a hypothesis that we test. And we start out with what's called a null hypothesis. And let's say we're comparing two groups, our before group and our after group. And we might be comparing, say, something like a mean of whatever we're interested in measuring. The null hypothesis is basically saying there's no difference. So my intervention didn't do anything. That's the null hypothesis. Or my quality improvement program did nothing. There's no change. So that's the typical null hypothesis. And then we take our samples and we test our samples, and we look on the bottom there, it says, do we have enough evidence from our sample to reject the null hypothesis? And so that's a formal way of doing frequentist statistics. And so there is if we are seeking an intervention that works, we would typically be seeking to reject the null hypothesis if it works, that there actually is a difference, which is the alternate hypothesis. And we formally say we will reject the null hypothesis and accept the alternate hypothesis that our measures are actually significantly different. That's the typical mode of frequentist statistics. Let's go to the next one. And so if we're trying to infer something to a population from our sample, everything then hinges on the sample. So you can see there that there's a few little humanoid people there, and that's our sample, and there's a bigger one over there on the left. So we're taking a sample from a bigger population in order to analyse our sample to infer something about the bigger population. So that's the inference side of statistics. Let's just have a pause for a moment and think about a hospital situation. Say for quality purposes, you may not be inferring to a population at all, because this is the subject of interest to you, the actual business of the hospital. So you're not trying to use the hospital here as a sample of a bigger thing necessarily. You're interested is in changing things here. And so you might collect every admission of a certain type. And so you're not interested in inferring anything with inferential statistics. What you've got is what you've got. And the mean of what you got is the mean of what you've got. And it's known to you. You're not inferring something in a population. So the inferential statistics for you is actually not going to be necessarily relevant. And so what you're doing, if your data collection is everything of interest, like a hospital, surgical type or whatever it is, because that's the focus of your improvement, then the mean or the length of stay that you are assessing is the length of stay. You're not estimating anything, you are knowing it. And so there's no inference there. There's no inferential statistics at all. And so what you'd be doing from that kind of activity is doing descriptive statistics. How do I best present what I just found in my surgical admissions? And so then you're doing descriptive statistic presentations, and then you're interpreting what you see. So is my mean or whatever it is, length of stay, is that real quality improvement, or is it just tinkering around the edges? And that's for you to interpret. So whether you're inferring back to a population from a sample depends on what you're doing. But in research, we typically take a sample from a broader population and then try and generalize it to the population. That's what most research does. And so in the sample, we will estimate something, or we will analyze something, and it could be a mean, and it shows there as X bar in the little sample. And what I'm trying to infer is the population mean, which is the mu symbol underneath the population there. So I'm using the sample to infer something about the broader population. Now, as an example, I've been involved in a study at Bendigo Health, which is the workforce COVID resilience study. And so in the study that I had joined later on, we had invited every healthcare worker in Loddon Mallee to participate in a survey. So what is the population? The population is every healthcare worker in Loddon Mallee, and we had the email addresses of all of you, courtesy of the health services, and then invitations went out from a big email list to everybody in their work email, and that list that we used is called a data frame. And then we sent out an invitation to every healthcare worker in Loddon Mallee, and then those who responded and said, yes, I'm willing to be part of this survey, I consent, and I've now been registered in my PICF, my patient information and consent form. Thank you. Those people who responded with consent became the sample. And that was about 2,000 people or so out of 8,500, 9,000. So the sample is about 2,000. The sampling frame is about 9,000. And it just so happens that the sampling frame and the population were the same because we had email addresses for every employee. So the people who respond to a survey like that, can we just move on to the next one? Oh, I'll go back. I'll go to that one in a minute. With the people who respond to a survey, is that sample representative of the whole workforce is the key issue. And so people, and what we found is that nursing staff who don't have much time, who come in for a shift, do their shift, and they just want to go home, they responded to the survey proportionately less than the population, because we knew the population from Department of Health stats. Allied health staff had more time on their hands in front of a computer and proportionately answered the survey more than their proportion of the population. So, and then admin people were about the same as the population proportionally. So we had a bias in the sample. And so in Frequentist Statistics, we generally assume random sampling so that our sample reflects the population and there's no bias. So can we just go to the next slide? And an example that's a bit topical at the moment is the sampling in the US presidential election. And that slide there is a screenshot from the 538 website that tracks multiple polls throughout the USA and summarises them and averages polls to get averages. So it's an average of averages. And they try and estimate, which way people are voting over time. Just before you move on, can you see, it's really hard to see, but there is over on the left-hand side, there's a thing called sample size. There's a column called sample size. And so it's about 1,000, can you see? It's about 1,800 or something. Oh, that's a good, I can see it here, can't we?
Yeah. Good one down, just one down.
So the top one is a sample size of about 3,000 something. The next one down is 2,000 something. The next one down is 1,000 something. The two on the bottom are 800. And so that's a sample of 800 people out of a population of 340 million. And you're trying to guess from that, infer how the whole population will vote. And so there's a lot of uncertainty about that because the people who are responding to those polls are again doing it by phone poll, and those who are more likely to behaviourally respond to a survey on a phone will take that survey. But does it survey everybody who don't have that behaviour? And the answer is no. And so the polls in the last couple of elections have been a bit off, to put it mildly. Let's go to the next one. And so the same website tracks the two main candidates. And what they've got there, which is really interesting, is they've got a solid line. If you look at when you get these slides, there's a solid line inside the blue bit there, and there's a solid line inside the red bit. And in the blue bit, there is a light blue zone around the middle line, which is the zone of uncertainty. And the same with the red. And what those two zones are the 95% confidence intervals. And that's a way of saying we are 95% confident that the real voting intention is in this band somewhere. But even then, it's only 95% confident. There is still, just through chance alone, the actual intention to vote for one of those two candidates can be outside that zone 5 times every 100. And that's not even taking into account our sampling bias. Let's go to the next one. So there's a summary of a population, a sampling frame, and the sample. And I've just given you the example of the COVID resilience study. Next one. So with sampling, one of the things that over the years, people who approach me to assist with their research project, sometimes quality people, but researchers, the issue of sampling always comes up. And sampling in Frequentist Statistics is assumed to be random. And is it really random is the question. And so you've got to know something about your population even to know that. And one of the things that I come across repeatedly in assisting people with their research projects is that they've introduced biases in their sampling. And so you can have various sampling methods like convenience sampling. Just the patients I treat is one convenience sampling type. Another sample is quota sampling. It's the first 100 females with asthma as the example up there. Purposive sampling and snowball sampling, the worst. There are various methods on that, but sampling is something that we do in the design part of our research up front to minimise bias in our sampling if we want to infer something about the population. If we get a bias in our sampling, our results will mean nothing. It'll just be a biased result. And
non-probability is used more with qualitative and mixed methods, is it not?
Yeah, it depends what you're doing.
And it depends on.
But if we're wanting to infer something about the total population, and this resilience study is an example. So we wanted to work out the factors that enable people to be more resilient as through the experience of COVID on the hospital and on their working lives and on their personal lives. And so if we say from the data, one of the things I remember is that there was a direct resilience psychological instrument. And one of the interesting things about that was which employee group would be the most resilient according to a self-administered psychological instrument. Would it be medical staff, nursing staff, allied health staff, or administration staff? And the answer was medical staff showed the highest resilience. But they were the smallest sample group. And so, of all of the junior doctors who were here at the time, were the ones who were most enthusiastic and okay about their workplace, were they the ones more readily, more willing to do the survey itself? And so does a personality type come in to doing the survey, which is also the same as their resilience during and after the COVID pandemic? And that was actually quite we spent a year looking at biases in the sample, a year. And then can we do that in a follow-up with junior medical staff? Well, no, because most of them have moved on, haven't they? They're not here anymore. Next one. The sample size. So one of the biggest questions one of the most frequent questions I get is when somebody is thinking to do a study for their master's or their PhD or for their work is, I'm going to take a sample. How big does the sample need to be? There's no standard answer. So because there are three factors that bear down on working out what is the optimum sample size, and that is the type 1 error, or our p-value. The second one is the power of the statistic. Another one is the effect size, and all of those three things mesh together to determine the optimum sample size. So there's a free program on the internet called G-Power. G-Power takes those three factors together and calculates for the statistical test you're doing the optimum sample size. So as an example, if I'm looking at something where I'll do an intervention and I know that the intervention will change whatever I'm measuring only a little bit. And so I need a large sample size to have the sensitivity to detect a small change. If I expect a dramatic change, then my sample size can be quite small and might only be 30 or 40. And that expected change from post to pre to post is called the effect size. And so if I've got a large effect size, my sample can be small. If the effect size is little, then the sample size can be very large. A very good example of that was the study done on low-dose aspirin as a preventative for heart infarcts. And a very big study was done of 62,000 people, very large sample. And when they calculated for those people who did have low-dose aspirin to those who didn't, did it change the incidence of heart infarcts? And the answer was yes. It was statistically significant that it worked. And so the study came out, hit the media, and the media got hold of this conclusion, and it became part of popular myth that low-dose aspirin will prevent heart attacks. And now I notice in the pharmacies, you can go up to a rack of aspirin and it's got low-dose aspirin. This is good for to prevent your heart attacks. It's literally a stand I've seen in a pharmacy, and it comes out of one study. What is interesting about that one study is that the sample size was so big and it was so sensitive that it came up with a mean difference in heart infarcts. But does it mean anything to a punter like you and me? The answer is no, because the effect size was so small, it was like winning the lottery. And so there's an aspect of these effects in healthcare called clinical significance. So was it clinically significant? And the answer is no. Let's go on to the next one. So coming back to if you've got everything you have in your quality improvement cycle, this is just one slide on descriptive stats and data visualization. So for people down in the quality department, presenting descriptive stats in a nice, colourful way is probably a good thing if you're going to convince people to do quality improvement. So jazz it up, make it look sexy, and people will get on board. That's the message of that. Just have it in easy to understand formats so that decision makers can make a decision. And so the command center thing that we were talking about earlier is totally about data presentation in easy to consume graphs for decision makers. Next one. Oh, no, let's move on. We've talked about that. I just want to introduce you to, this is not to be remembered or consumed. In statistics, there are 5 main groups of statistical tests. There are over 100 statistical tests, and I don't remember them all. No one can remember them all. There are groups of tests, associations and correlations, predictions and relationships, group differences, one sample, and reliability. Reliability can be useful in quality, so I can talk to you about reliability tests if you wish. At some point, it's useful to your department. For research, one of the main things, one of the main useful things in statistics for researchers is predictions and relationships. So a lot of that, you've heard of regressions, data regressions, linear regression, logistical regressions and things like that. Those kind of techniques are useful when you have a whole bunch of variables and you want to be able to see which variables affect other variables. So the ones that do the affecting are called independent variables. The one that gets affected is called a dependent variable. And so you might have something like length of stay, which is like the end of a chain of causality. And that could be a dependent variable, but what factors bear down and influence length of stay? That might be what you're interested in. And that is a constant thing in the hospital setting. What is it that affects length of stay? And how can I improve those factors that affect length of stay to minimize or to optimize length of stay? That's one thing. Group differences we've talked about, which is pre and post, or an experimental group and a baseline group. And if I just go into the next one, just really quickly. So this is a decision tree about which statistical test do I use. These are the groups, and you can look at that later when you get emailed this presentation. Just go to the next one. So that's an example of associations and correlations, and those pink boxes are all different statistical tests. And that's a decision tree as to which test do I use given the data I've got. And you don't need to consume that now. It's just know that there are a lot of tests. Next one. That's a different decision tree with a different bunch of tests. Next one. Different one again. The pink ones are different tests. Next one. Pink ones, different tests. So you can see that there are a lot of statistical tests out there. And one or more of them are going to be suitable to your purpose. And so this decision tree thing here is something I use. And if you're considering doing statistical work, then I can sit with you and we can work out which is the best approach to analysing your data, because there are so many options. There are over 100, there's something like 150 statistical tests in Frequentist Statistics alone. And I don't know how to drive all of them. Nobody does. And so that's why the stats community on the internet is huge, because no matter how skilled you are in statistics, there's always something more to learn. So the learning journey never really ends. Let's just flick through to the end. Next one. Oh, just coming back. Common issues. I've mentioned a few of them. I just want to mention one thing about missing data. One of the things that I get a lot from researchers in Bendigo Health is they collect data and there's a lot of missing values in different variables. And the more missing data there is, the more uncertain your results are going to be. The more biased your sampling is, the more uncertain your results are going to be. The more outliers you have, the more uncertain your results are going to be. And that's not even taking into account, there's a third from the bottom, statistical test assumptions, so that in those 100 tests, each test has its own set of assumptions that need to be ticked off for that test to be used in a valid kind of way. So one of the things I just finish off with, just go on to the next one. It's very hard to explain. If I had more time, I'd explain it better. But just in terms of missing values, one of the things that we do sometimes with missing values is we interpolate missing values to make the data set complete. And we try and learn from what data is there, how to populate missing values on a best guess basis. And the point of this slide and the next one, which we won't do, was that I tested interpolation in 2 statistical software programs to see how they performed. And I used SPSS to do interpolation, and I used R to do interpolation, a particular statistical program called R, and they interpolated differently, and they interpolated effectively differently. The more missing values there were, SPSS performed more poorly. And the algorithm in R performed slightly better. So again, this is about, I was going to highlight the choice of tool. So which statistical software are we going to use to work through our statistics? So there are horses for courses, and some of these software tools are better than others. So that's all I was going to say, to introduce you to the complex land of statistics. Can you just go over one more? One more? One more? That was just interpolation. One more? One more? Oh, I missed the one with the crystal ball.
Oh no, that was there.
Was it there?
That was
it?
your list of common issues.
Yeah, and it says
black art.
Statistics is a bit of a black art.
Yeah.
Yeah. So that's all I was going to say. And then we can just have a chat if you wish. And if you're a bit brain dead, then we can all go home. So thank you for coming. Can I just say just about statistics and something that is coming up in my work soon. It's started already. The executive here are interested in a Bendigo Health Command Centre, so the whole of hospital business in real time on one big screen, so that we can see the patient flow in real time. And the bed managers can best use that information to optimise the flow through the hospital. At the core of that command centre is statistics. And so statistics is there to estimate or to guess what is going to come through the door in 12 hours, in 24 hours, so that we can be proactive rather than reactive. And then it will also look at the best way to queue patients within the system. And that will be based on statistics as well. So everything is based on statistics. So that comes under a heading of machine learning. So we are going to learn our patient flow from our patient flow history, and then work out, given the history, what is the best way for patient flow to work now? Where do we move patients now? Because this is coming through the door in the ED. So we'll be working, I'll be working with the CSIRO on that. And the CSIRO approach is all statistical. So it's important. It's important in our lives. And I think patient flow is one of the biggest issues we have, isn't it? Is it not? In the hospital, one of the biggest practical issues we have. And so that's all statistics based. It's about modelling our patient population.
There are a number of confounding factors.
There are lots of confounding factors. That's right. Yeah. And that's why a bed manager can't hold all those factors in their head simultaneously. It is not humanly possible. There are too many dependencies on dependencies on dependencies. And that's the idea of running through scenarios 1,000 a minute, so that the bed manager doesn't have to do that. That's right. So if we can take the burden off the bed manager's brain, then the bed manager can probably do a better job with the freed up time to actually do the bed management. Yeah. So just in terms of where to from here, I'm probably one of the full-time statisticians at Bendigo Health. At Cancer Centre, do you have a statistician? Does Linux have a statistician?
They've got a lot of data analysts and people who can do it. Yeah, I'm not sure if they've got dedicated.
Yeah, whether it's just data handling or
Yeah.
statistics is their main thing.
Yeah.
Yeah.
I'm not sure there's something.
There are a few analysts there, aren't there? Yeah. Do you know Sharon? Anyone else?
No, not
Limix
now.
was the only one I knew of that might have a statistician.
Mm.
So people who do research across Bendigo Health normally who need assistance will come to me, and that's fine. I'm very happy to sit down with anybody and work through their proposed project. And it also helps get the statistical planning is also part of the ethical application planning and getting the ethical application together. So I often help people with both of those things. And that's my job.